Hi everyone, welcome to our final video in the module on correlation and simple regression. We're going to be talking about causation and association today. So in the previous videos we had talked about, correlations and causal relationships, and that, correlation doesn't necessarily mean causation, and we want to expand on that idea a little bit and give you kind of a primer on some conceptual issues that are going to become important, especially if you advance your career in statistics with observational data and looking at different types of advanced regression models. So first, right, you probably have heard that correlation is not causation. Not only did I say that in a previous video, but it's kind of a fun catchphrase for people, and someone reports a correlation and someone makes a causal interpretation of it, right? People will be quick to say, correlation is not causation, and that's a logical error. And most of the time that's true. Well, correlation usually is just describing an association, and a lot of the time we don't actually have a good reason for interpreting the direction of that association or a causal nature of that association. We can just say that two things do reliably seem to co-occur together. So while most of the time I would say this is correct, I think it's also important to remember that correlation is not causation. By which I mean, sometimes correlation is because things are causally related. Not all associations are causal, that's definitely true. But it's also true that all causally related phenomena will have an association. So evidence of an association is not evidence of causality in and of itself, but it is important to remember that two things being related is an important step in establishing that they are causally related. And often we need more data or more information to really help kind of rule out alternative explanations. But just because two things are correlated, it doesn't mean they're not causing one another. So one of the things we have to consider anytime we're looking at these kinds of associations is that there are lots of different types of association. And usually, if we're conditioning our predictions on a single variable, that won't actually be enough. We've introduced this idea with simple regression in the last couple videos, but one of the problems with that, right, is that most variables that we might measure, whether it's height, academic achievement, the probability of winning a game or something, are being caused by multiple factors, or even if they're not caused by multiple factors, they're probably associated with multiple factors. So very seldom is there only going to be one variable of interest that we have in conjunction with some outcome variable, right? So we're going to have to start thinking about how we can build more and more complicated models to reflect more and different types of associations. But let's think about this kind of simple relationship, right? Where if we just had a random variable y, and the only thing that related to it was x1, if we regressed y onto x1, right, so y is equal to an intercept plus a slope times x1, then any error between those two would be due to measurement error. And we would say, okay, well, that's the error term of our model. But one of the things that could happen, right, is that we might have x1, and so we can get x1's relationship to y, but there are other variables that we haven't accounted for that might be explaining part of y. And at the moment then, deviations in y that are due to x2 and x3 will show up in the error term, but they're not really errors in that sense. They're not random fluctuations. Those are things that are due to systematic factors that we just haven't accounted for. So you could say, well, we'll account for those variables, right? We'll put those variables in our model and we'll build a multivariable regression model rather than a simple regression model. And that will be a better approximation of y. And you're correct in the sense that that will probably lead us to a better approximation of y, and it's going to reduce the size of the error term. But there are still variables that we probably just aren't going to be able to account for, right? So at the end of the day, what we're calling error in that data equals model plus error framework, right? That error is from many different sources. That error can be due to things like measurement error in y. That error can be due to unaccounted variables that we haven't considered, right? And you might feel like you want to chase down all the variables that actually have an effect, but that's oftentimes not necessary because many variables that we might add into our model might not really be related, right? Or they might complicate the relationship, or we want to think very carefully about how we're building these models and what variables that we're putting in, because the answer is almost never just build a bigger model and throw everything at it. So Further, the other thing we want to consider then is beyond the number of variables that we're adding in is how do these variables relate to each other? And this is really how we get to this issue of causation. Because causation, as we've said, is not established by the statistical relationship, but by a logical analysis and or an experimental design, right? There are whole disciplines where you can never conduct an experiment, but we can have pretty strong theories about what causes something else. Right? So geology and plate tectonics, right? We can't conduct experiments on plate tectonics, or astronomy and the motion of interplanetary bodies, right? We can't conduct experiments on those things, but we can still develop very strong causal models based on a logical analysis of associations. So a lot of the time, we put a lot of privilege on randomized controlled trials in the biomedical field. But I do want to point out that you don't necessarily need a randomized controlled trial in order to make inferences about causation. You just have to make sure that all of your kind of assumptions are met and you have a reasonable model for starting to draw those inferences. So let's consider some complicated types of associations that we might have to tease apart if we're really trying to understand some kind of causal relationship. So one thing that we might have, right, is something where both x1 and x2 cause y. So in that situation, x1 would be associated with y and x2 would be associated with y. Now, x1 and x2 might not be related to each other, right? But each one is going to make a unique contribution to the variance of y. Because if x1 goes up while x2 stays the same, maybe y goes up. But if x2 goes up while x1 stays the same, y still goes up. So we'd have to account for both x1 and x2, and they would both be associated, and they could both be causal. However, right, we have to be careful because that's going to look a lot like, something else like this. So we could say, okay, well, x1 actually causes x2 and that causes y. So that, if we just looked at x1 by itself, would look like it's associated with y. And if we looked at x2 by itself, it would look like, that's associated with y. And we would actually need to build a model that accounts for the fact that x1's relationship to y is actually because of x2. And x1 is causing a change in x2, right, which is causing a change in y. But then we'd have to examine each of these linkages, right? And say, well, is x1 really causing x2 or is x1 really associated with x2? And at each of these stages, right, we'd have to worry about, well, is there another mediating factor, right, in the linkage between x1 and x2? Is there an x3 that lives somewhere over here? Similarly, right, we might have an issue where x1, x2, and x3 are actually all caused by an unmeasured third variable, which I'll call z1. So in this situation, if z1 is causing all of these, then if z1 changes and x1 goes up, that's also going to cause y to go up. So it's going to look like x1 and y co-occur together and they're associated, but they're not actually causal because it's the z variable that's actually causing that relationship, right? So we have to be very careful anytime we observe an association to establish the causality. And most of the time when we're working with observational data, correlation is not causation. We have to be very careful that we're actually just treating these things as association, and we have to be pretty humble about any assertions that we can make. We can't say which one of these things is causing the other. We can only say that they're associated. Now, that can go a little too far though, right? Because again, correlation is not causation, but also anytime something is causal, those phenomena will be correlated. And I really think this XKCD comic summarizes that quite well, where the one character says, I used to think correlation implies causation. Then I took a statistics class and now I don't. And the other character says, sounds like the class helped. Well, maybe. Right? Like clearly, if you learned that in the class, that association seems like, well, the knowledge you gained in the class changed your mind. That's a cause, right? But I think it kind of just highlights you can take this correlation is not causation attitude a little too far. We want to be trepidatious, right? And we do want to be careful that we're describing things as associations and not over-interpreting them. But we also want to recognize that hey, sometimes evidence of an association is the first evidence we might have that things might be causally related, and that can merit further investigation. And if we're willing to build sufficiently detailed models, we can actually start to chip away at causal explanations, provided our models are robust. So in general, we want to be careful and avoid causal assumptions of observational data. It's far better to say, that variables x and y are associated, and when you're writing up those kinds of results, don't assume that, adding more x is going to yield more y. However, we also have to remember that causality is not established by the choice of the statistic or the significance of an effect. It depends on the research design and adequately controlling for confounding factors. This is why we like randomized controlled trials so much, because good randomization in big samples is really helpful for balancing groups on the potentially confounding variables that we haven't accounted for. But RCTs are not the only tool for establishing causal relationships. There are structural equation models and causal inference models where, using observational data, you have to build pretty complicated models and protect yourself against kind of all the known confounders, but you can start to make more causal claims based on purely associational data. We also want to avoid privileging RCTs so much, because it's true that RCTs are a great tool for establishing causality when all the assumptions are held and all bias is reduced, but they can also be very incorrect or misleading if they're poorly designed. So we shouldn't just trust something simply because it's a randomized controlled trial. We have to ask, was it a good randomized controlled trial? And then we can get an association between, for instance, the administration of a drug and an outcome, and we can really say robustly, well, administering that drug caused the change in the clinical outcome.